Glasgow. Now, Glasgow is not just Glasgow. Glasgow is divided in two parts. There's the Celtic part and the Ranger part. And he definitely is part of the Rangers. He grew up at the University of Glasgow, maybe a bit inspired by his older brother that studied physics, but then unfortunately young David, didn't go all the way to physics, but went into chemistry, fortunately for us. Then he moved to the US, did a PhD at UC Irvine, went to Harvard for a postdoc, and that's when he had all the asymmetric catalysis in his genes. He started his independent career, got in 2000 the first organic molecule and you've known the rest. I think one of the impressive parts of our plenary speaker is that he's not only known as one of the fathers of organocatalysis, but he kept being active in all types of synthetic chemistry. He's been one of the pioneers in photocatalysis and many other domains. So please join me in welcoming Sir David MacMillan on stage. Thank you.
Thank you, Martin, for that very, very generous introduction. Let me also point out, when someone's given a talk in Dublin, don't tell them that they're a Ranger supporter. You know. But honestly, it's fantastic to be here. I also have to thank UCD for sponsoring my lecture today. And I also have to thank Professor Pat Geary for not only being a tremendous friend, but also for many, many times I've come to Dublin and just had a fantastic time, and it's all because of Pat, and this time has been absolutely no different. Okay, so thank you all for showing up on this rainy Tuesday afternoon at 5 p.m. I know it's late in the day. I was trying to decide what kind of talk to give. I was thinking about, should I give a very general talk, which is kind of fluffy, but isn't really that organic chemistry focused, or should I give a really technical talk? And I couldn't quite decide, and this morning I thought, well, I'll give a really hardcore technical talk. But then I was also sort of inspired by Frances's talk yesterday, where she beautifully weaves in some of the things that's happened to her over the last few years in her talk, and I thought, well, it'd be nice to do that as well. So I thought I'd sort of cut the difference, and so I'm going to talk for 40 minutes about organic chemistry, things we've been working on, and then for the last 10 minutes, since it's getting late in the day, I thought I'd tell you some stories. Hopefully they're amusing stories about what it's been like for me for the last 2 years or so. Okay, but let's start off by telling you what I'm going to talk about, which is photoredox catalysis for chemistry and biology. Now, as Mark mentioned, I was very lucky to be honoured for working in this area, organocatalysis, which is a field that we were excited to be part of along the way. But to be honest, that's not something that we've been heavily working on for the last 15 years or so. What we've really been working on is photoredox catalysis, which is an area that I'm really going to spend most of my technical talk discussing this afternoon. But although these areas seem quite disparate from each other, they were really one was the foundation for the other. If we weren't doing organic catalysis, we would have never ended up working with photons along the way. Now, what are we doing with photons? Well, what we started doing, I think it was about 18 years ago now, we started thinking about the way physical inorganic and inorganic chemists were developing all this wonderful knowledge about how to try and power the planet using solar energy. And we started to ask ourselves, could we take some of that knowledge and export it over into organic chemistry? And that led us into this world of photoredox catalysis, which I'm going to talk about mainly this afternoon. And one of the nice things about photoredox, and many of you who do photon-driven chemistry, is beyond the fact it's a great area to work on, it allows you to make these really nice, attractive videos that you can sort of show the audiences, especially people who don't work in this area. But photoredox has been a really interesting area, and I would say over the last 2 or 3 years now, a question that I'm often asked is, why do you think photoredox is sort of taken off as a field? If anything, it's simply, I would argue, as big, if not bigger, than the field of organocatalysis at this point. And it's an interesting question, why did it take off? Why did it become a reasonably significant area? And there's many different reasons, but the reason, at least that resonates most with me, is the idea that it allows effectively to use native functional groups or chemical feedstocks in a way for chemistry that we haven't really used, especially for organic chemistry before. So why is that? Or why is that important? Well, one aspect is that these native functional groups or chemical feedstocks are available around the world in tremendously diverse structural format. They're really available in lots of different structural entities, but in many ways we haven't been able to utilize them as much as we would like to. So why does photoradiomics allow us to utilize them? Well, it's basically because of these types of catalysts. So why would that be? Well, let me show you this sort of point. So if I take my hand and I shine this blue laser pointer on my hand, I can do that all day long, and it won't do anything to my hand. It won't hurt it. I'd look a bit silly doing it, but it doesn't hurt me to sort of do that. However, if I shine blue light onto one of these photocatalysts and it goes into the excited state, it becomes the equivalent of 32,000 degrees Celsius, while everything else in the reaction vessel is at room temperature. And that sort of non-equivalence of energy, the catalyst has to deal with that in some way. It has to offload that energy. Now, one way it can do that is to release a lower energy photon, but the other thing it can do is either energy transfer or it can do electron transfer, which we're going to talk about today. And because it can take electron transfer, it can take molecules that we think of as being in a pretty low ground state and then move them up to a really high energetic state. In this case, is basically radicals. And one of the sort of critical features of this, although radical chemistry has been known for a very long time, typically we would think about how you create radicals. We usually think about high energy start material, an azide or some sort of diazo. In this case, we're effectively taking really stable bonds, but creating really high energy species just by channeling photons through these catalysts to reach them. Now, once we can take these really structurally diverse formatted molecules and make them into these high energy systems, we can then start to invent completely new chemical reactions. And one of the values of this has been the adoption predominantly by the pharmaceutical industry. There are over 500,000 medicinal chemists around the world who every day are doing different chemical reactions from each other. And the availability now of this structural diversity to them in commercial formats now allows them to plug and play as they try to go about performing drug discovery. But it's also true of other areas, agrochemistry, fine chemicals, you name it. People are now utilizing these reactions for a whole host of different systems.